Hi, my name is Satish Singh. I'm working with Dr. Carol Flanagan and Deviate, an MDP research team focused on machine learning research. And I'm here to present my Capstone project, a frame skipping algorithm for efficient data processing. Before I go into what exactly frame skipping is, allow me to briefly go over the motivation behind the project. So Deviate, as with a lot of research teams, often runs into a major bottleneck when it comes to the process of labeling data. When collecting your own data, it's often necessary to go through each image or video collected and label all of the objects of interest. And since data sets for training machine learning models can contain thousands of images or hundreds of videos, this can be quite a lengthy process. This is especially true for small research teams, which often don't have the resources necessary to hire dedicated labelers or to crowdsource their labeling efforts, which means they often have to face a trade-off between incorporating larger, more diverse sets of data and working on tuning other aspects of the model. In the long run, this can lead to underperformance of the model. As such, the goal of my project is to make the labeling process more efficient, freeing up time for researchers to work on other aspects of the model or to incorporate larger, more diverse sets of data. One major source of inefficiency that I address with my project is the idea of frame redundancy. So in video data sets especially, since cameras can capture many frames per second, what often ends up happening is that there are consecutive frames that look almost identical. In addition, depending on the data set, there can be long stretches of video in which the environment is basically stationary, nothing is really happening. For example, Deviate deals a lot with analyzing and identifying driver behavior behind the wheel. So a lot of their videos contain stretches in which the driver isn't really doing much and the environment is basically stationary. For example, here is one example of 2 frames from a video from the data set in which the environment is basically stationary between these 2 frames and between the 20 frames that came in between. Now, the issue here is that after you've labeled the first frame in this stretch of video, labeling the additional frames is time consuming and doesn't really add that much information. And when you're dealing with a data set that's hundreds of videos long, having to label all of these redundant stretches of videos can take a lot of time and frankly isn't a very great use of time since you're not gaining much from it. So this is where the idea of frame skipping comes into play. If we can consistently identify these redundant stretches of video, we can direct the labeler's attention to only the frames which are actually important to label. And if we need to use the full data set, we can use a simple interpolation scheme to propagate the labels to the rest of the set rather than having to label everything by hand. So in order to detect these unique and redundant frames, I extract key features from an image, such as corners, edges, or other visually distinct, easily identifiable and trackable points, and I track their motion throughout a video. For frames in which these key points move significantly from the previous frame, I label the frames as unique and hand them to the labelers for manual labeling. Otherwise, the frames are labeled as redundant and are skipped. The unique frames are labeled, and using those labels, we can use a simple interpolation scheme to, as discussed before, propagate the labels to the rest of the set. I experimented with several different key feature extraction and interpolation schemes, and the final algorithm I prepared uses orb key point extraction to detect the corners and edges, and linear interpolation to interpolate the labels to the rest of the data set. So at a high level, the algorithm I designed consists of 2 components, a frame skipping component and an interpolation component. The frame skipping component takes the video we want to analyze as well as a few threshold parameters as inputs. The threshold parameters are used to determine whether a given frame is unique or not. We iterate over each frame in the given video file, detecting the key points in the newest frame as well as the last unique frame, and we match as many key features between the 2 frames as we can. If there are very few matches, or if the matches that are detected have moved significantly from their previous position between the 2 frames, the newest frame is labeled as unique. In either case, we can determine that the environment has changed significantly, and so it's worth looking at the newest frame. Once we've detected all of the unique frames in a given video, the frames are handed to the labeling team, and using the list of unique frames and the manually generated labels, we can interpolate the label positions throughout the dataset, allowing us to use a full dataset without having to label everything by hand. So in order to test this algorithm, I ran the algorithm on a subset of 50 videos that basically track the face view of a set of drivers while driving. So basically it's looking at um, where they're looking while driving, whether they're looking at their cell phone or outside. The videos themselves range from a few seconds to over 10 minutes long. The videos are all black and white, as seen in the earlier examples, and the dimensions of each video are 300 by 448. The features of interest in these videos, the things we want to label, are key facial feature positions, such as the eyes, mouth, and nose. And the videos I tested on were fully labeled. In addition, in order to figure out what the optimal performance is in terms of the optimal set of threshold parameters, I implemented a grid search algorithm to test different combinations of parameters to see which worked the best. I assessed the algorithm based on its accuracy, basically how close are the interpolated labels to the ground truth, and time. How long does it take to run the frame skipping algorithm, and how many frames do we need the ground truth labels for in order to achieve the optimal performance? So the idea here is that we're expecting to save time using the frame skipping algorithm, but at the cost of some accuracy, since the interpolated labels are likely to be less accurate than if we were labeling everything by hand. But the goal here is to see whether the benefit we see in time justifies the loss in accuracy that we see, and whether in the long run, this algorithm is worth using over manual labeling. So in terms of speed, the algorithm runs fairly quickly. I found that the time taken to process the video scales linearly with the length of the video. And I found that the algorithm can process roughly 75 frames per second, regardless of length. To put that into context, the longest videos in the dataset, which were roughly 13 minutes long, took just under 2 minutes to fully process, which is really quick. The caveat here is that these times reflect how long it takes to process the video a single time. When using a grid search algorithm, you have to run the frame skipping algorithm multiple times in order to find the optimal set of parameters. And so the frame skipping process, even if it takes a short time to run once, needs to be run multiple times, and so can take longer to sort of figure out what the optimal performance is. Right. So in terms of accuracy, as expected, we did see a noticeable error in terms of the position of the interpolated labels as compared to the ground truth labels. This error is worse than human error, and there's a lot of variance from video to video, as seen by the significantly large outliers that we have. This variance is often caused by having some videos which have a lot of sudden motion or sudden changes in the environment, such as the lighting, which affect the accuracy of the key point tracking. However, generally compared to the size of each frame in the video, the error isn't too large, and we're able to achieve this accuracy by using roughly 50% of the ground truth labels on average, meaning that we can save up to half the time we would have normally spent manually labeling if we instead use a frame skipping algorithm and only focus on the unique frames. Okay. So far, the results look very promising. The frame skipping algorithm cuts down on a lot of the labeling work when compared to manual labeling, and the performance of the interpolation algorithm is reasonably accurate. However, there are still one or two tasks I'm working on. First, I'm working on training a machine learning algorithm using the interpolated label data and comparing the performance of that model to one that was trained on ground truth data. I want to determine whether the error in the interpolation phase affects the performance of the model significantly, because that could affect the feasibility of the frame skipping algorithm in the long run. In addition, in the future, I'm planning on working on improving the accuracy of the frame skipping algorithm, by detecting and ignoring the key points that are consistently static. This will allow the frame skipping algorithm to focus only on the parts of the frame which we would expect to move, and could result in better, more accurate detection of unique frames, which would in turn improve the accuracy of the model. Thank you for listening to my presentation.